Okay, here's the quiz review for 2.4 to 2.6. Number 1, the distribution of weights of female college cross-country runners is approximately normal with a mean of 122 pounds, standard deviation of 8. What's the following is the closest to the percent of the runners who weigh between 114 and 138 pounds. So remember, when we do these, we always want to check to see are the numbers actually standard deviations away from our mean. So let's draw our rough sketch here. And we know the mean is 122. And I'm going to go 1, 2, 3 to the right and 1, 2, 3 to the left. Okay, standard deviation is 8. So as we go to the right, we're just going to add 8. So this is going to turn into 130. This is 138. And this is 146. And on the left side, as we move away below the standard deviation, we're going to subtract 8. So this turns into 114. This is 106, 2 standard deviations, and then 3 standard deviations is 98. Okay, let's see where we're at here. 114, okay, that actually is on one of our standard deviations, and 138 is as well. So we want the area between these two. So we just need to figure out what that is. Well, since these are on the empirical rule, they're on my standard deviations. So we know it's the 68, 95, 99.7%. So 114 is 1 standard deviation to the left. So we know that's 34%. And then 138 is 2 standard deviations to the right. So we know this is 34% here, and we know the next one over is 13.5%. So to find the area, we just need to add all those up. 34 and 34 and 13.5. That ends up giving us 82. Well, it's about 81.5% is what it actually is. But when we look at our choices, it just wants to know which one is going to be the closest one. So what's closest to 81.5? Of course, that's going to be 82. Okay, looking at problem number 2. A student obtained a z-score of -140 on a national test for which the mean was 500, standard deviation was 50. Find the student's actual test score. Okay, so we're going to use our formula that we've all been studying. So the z-score, which is a -1.4, -1.4 is equal to the actual test score, which we don't know, minus the mean, which is 500, divided by our standard deviation, which is 50. Okay, to divide 50, of course, we're going to have to multiply by 50. So multiply both sides by 50. I'm going to get that out of our answer choices. These are going to cancel out. A -1.4 times 50 is a -70. That's going to equal x minus 500. And then add 500 over to the other side. And we end up with 430. And if you look at your choices, 430 is B. Okay, number 3. Fastball speeds in collegiate baseball are normally distributed with a mean of 86 miles per hour, standard deviation of 4 miles per hour. Suppose that Major League Scouts will only consider pitching prospects who can throw a fastball at least 90 miles per hour. What percentage of the pitching prospects who are considered can throw at speeds over 95 miles an hour? Okay, on this one, we're going to go ahead and give ourselves a sketch here. Now this one is a little bit harder to think about, so we're going to have to talk about this one. So we know that the standard deviation, the mean is 86, and the standard deviation is 4. So if I went 1 to the right, I'm at 90. If I went another 1 to the right, I'm at 94. And if I went another 1 to the right, I'm at 98. So here's where we kind of run into a little bit of problem. The first part of this problem is talking about they have to throw at least 90 miles an hour. Well, 90 is one of our standard deviations. So that would be this area right there. So because that's a standard deviation, we could figure it out by adding up the percentages. The problem falls in, though, is that our second number, 95, is not a standard deviation. So when they're not both on the standard deviation, we have to find the areas of both of them and then do the percentage. So let's go ahead. I'm not going to be able to use the empirical rule again because they're not both on a standard deviation. So we're going to do a normal CDF. So do the normal CDF. Go ahead and grab your calculators right here. We're going to do 90 is our minimum. Infinity is our maximum. Standard deviation, sorry, mean was 86. Standard deviation was 4. So grabbing our calculators, we're going to go second bars down to normal CDF. Lower is 90, upper is infinity, mean is 86. Standard deviation is 4. Okay, and if we go through all of these, we get 0.158655, which should be pretty close because if I added up the standard deviations, that would have been 16%. So I know that's right on. Okay, now we're going to have to do the exact same thing, but this time 95 is going to be our low number. So we're going to go up to 95, so second vars down to normal CDF, and this time it's going to be 95. Everything else is going to stay the same. And there's our answer on this one. Now, the question asked for the percent. Let's just double check that. Yeah, it asked for what percent can throw at speeds over 95. So we need the speeds over 95 over the ones that are at least 90. So this just turns into a proportion right here. So the first one was the 16%, but it actually ended up being 0.158655, whatever. So if I roughly rounded this would be about 15.9%. So that is going to be what my denominator is, 15.9%. And then on our numerator, that's our other normal CDF, that was 0.012. So this would be about 1.2%. So that's going to be our numerator. And then all you got to do is grab your calculator and find out what your answer is. I just divided those two decimals. I got 0.077, so about 7.7%. And I believe that is our answer. Better be. Okay, number 4, kitchen appliances don't last forever. The lifespan of all microwave ovens sold in the U.S. is approximately normally distributed. Mean of 8 years, standard deviation 2.5 years. What percent of the what percent of the ovens last more than 10 years? Okay, very similar to the last one we just did. Let's go ahead and do a quick graph here so we can check to see if it is a standard deviation. Okay, so we know the mean is 9, and I'm going to add and subtract 2.5. 1, 2, 3, 1, 2, 3. So adding 2.5, and this one's not really going to take us too much because if we add 2.5, we're at 11.5. And our problem wants more than 10. So I know that 10 is going to be somewhere in here. More than's going this direction. So when I get ready to do this, we're going to do normal CDF again. So normal CDF. Our low end is going to be 10. Our upper end is positive infinity, so big numbers. And then our mean on this one is 9. Standard deviation is 2.5. All right, plug it in and see what you get. I think it ended up being something like 0.3445 something. And if we wrote that as a percentage, we would end up getting 34.5%. Okay, next page. Number 5, the mean age at inauguration of all U.S. presidents is approximately normally distributed with a mean of 54.6. Barack Obama was 47 when he was inaugurated, which is the 11th percentile of the distribution. Which of the following is the closest to the standard deviation of the president's age? To do this one then, we know what the percentile is. What we don't know is the z-score or the standard deviation. So we are going to use our formula. The z-score is equal to the value minus the mean over the standard deviation. So we are going to use this formula right here. We know that the 11th percentile is when Barack Obama was inaugurated. We know the value, so we've got the value is 47, standard deviation is 54.6. We do not know, excuse me, the mean is 54.6, the standard deviation we don't know. And we also don't know the z-score. So we're going to actually use the 11th percentile and figure out what the z-score is. So we're going to do inverse norm on this one. And I guess we should rough sketch this here real quick. So here we go. All right, here's our mean. That's 54.6. And then Barack Obama was down here at 47. And this area right here is 11%. That's the 11th percentile. That's what that's telling me. So what we want to know is what is that x value. That's what we're trying to figure out, or a z-score, so we can find our z-score. So inverse norm. So if you jump over to your calculator very quickly, we do inverse norm. The area is 11%. Mean is 0, standard deviation is 1, and we're shading to the left on this one. So if we come back through here, we get a negative 1.23. That is our z-score on a standardized curve. So we know what negative 1.23, we can round to that. So negative 1.23 is going to go in right here. Cross multiply and then divide, so you get your standard deviation is 47 minus 54.6 divided by a negative 1.23. After we did our division up here, we should have got 6.178, which rounds to 6.18. Okay, ACT scores are normally distributed with a mean of 21, standard deviation of 4.5. We're going to draw the normal curve, label out 3 standard deviations each direction, and then answer our questions. So we know that 21 is going to go in the middle, that's our mean, and then add 4.5 3 times, and then subtract 4.5 3 times, and come up with your number line. And these are the numbers you should have come up with on your number line. They want to know where 60% of all scores are going to be. 68% is 1 standard deviation away. So that would be between a 16.5 and 25.8. Sorry, that was 25.5. Okay, next one they want was 95% of all the scores. So that is 2 standard deviations away. That is 95% of all of the data right there. So that would be between 12 and 30. And then the next one says 99.7. That is 3 standard deviations away in each direction. So that would be 7.5 to 34.5. And then our last question, what percent lies below a 30? Okay, so here's 30, and we want everything that lies below it. Well, 30 is 2 standard deviations away, so you could actually figure out what's left over here and then subtract it from 100, or you could do all of your percentages to the left. If you went from 30 to the right, that is 2.5%. So then what scores would lie below that? We would just take 100 minus 2.5, and we would get 97.5%. Okay, assuming the heights of the college women are normally distributed with a mean of 65 inches and standard deviation 2.5, answer the following using the empirical rule. Okay, so again, you're just going to draw your normal curve. And 65 is our mean. 2.5, 1, 2, 3, 1, 2, 3. Go ahead and add and subtract 2.5 to come up with your number line. Okay, here are the numbers for your number line. Part A says, what percent of women are taller than 65 inches? Okay, so 65 inches taller gives me this direction. Well, that's half of our data, so we should have 50% there. Part B, what percent of women are shorter than 65? Okay, and again, there's our middle. Shorter would be over here, and that is also half of our data, so 50%. Part C, what percentage of women are between 62.5 and 67.5? Both of those are one standard deviation away from the mean, so we know that that is 68%. And then D, what percent of the women are above 62.5%? So that's all of that. And again, 50% is happening here, and I know this chunk is 34%. So add 50 and 34 together, and you're going to get 84%.